Okay, this is my video on day 2 of volume. So if you haven't watched the first video, you should definitely go back and watch that because I'm jumping right in. So basically, same process as what we're doing. These are just going to be more complicated examples, and you'll kind of see what I mean by that as we work along. So we're starting with a cylinder again. So we're going to do one question that we can do by geometry and calculus, and then we're going to jump straight to like ones that have to use calculus. So just kind of our introduction, take us back to yesterday a little bit. Y equals 3 and y equals 2. So here's what is happening here. There's my line y equals 3, and here's my line y equals 2. And I'm going from x equals 1 to x equals 5. So yesterday we had just the line y equals 3 and revolving that. We're adding this inner line, and I want you to almost think of it that way. So I said I like to start with just a reflection. So a reflection of this looks something like this, and then let's try to make this three-dimensional. So and if you're able to visualize that, we basically have a cylinder inside of a cylinder. So you can think of it as we have a cylinder and then we drilled out the middle of it is what's happening there. So we can do this, of course, using geometry by literally finding we probably did these more with area as opposed to volume, but the volume of one minus the volume of the other. So volume of the big cylinder minus the volume of the small cylinder is what I'm going to think of this as. So I have pi r squared times height. I'm going to use a capital R for that for the big radius minus pi r squared times height, little r for the inside one. And plugging in numbers there, so we've got the big radius is 3, and then the little radius is just, I guess I'll do it right here, 2 for that one. And then the height for both of them is 4. That's the distance from 1 to 5 is where I'm getting that. And that's the same for both of them. So giving us a calculation here, 3 squared is 9 times 4 is 36 pi. Minus 2 squared is 4 times 4 is 16 pi, giving me 20 pi when I subtract the 2. So using our calculus method, we're going to slice this into a whole bunch of slices or disc. But what's going to happen here is when I take that slice, so I want you to try to visualize taking a slice out here. And what's going to happen when I do this, if you can visualize this at all, I know this isn't a great picture, is there's going to be a hole in the middle. So we end up with what we commonly call a washer instead of a disc. So it's a circle with a hole in the middle. And what I'm trying to do is find the area of, in geometry we call these shaded region problems. I'm trying to express the area of the shaded region outside the inner circle, but inside the outer circle. And there's no formula for that. There's no one magic formula of what I can use. So I think of it as a subtraction problem. Find the area of the big circle minus the area of the small circle. And wait, why did I just switch to area? Well, we're finding the area of one of those, multiplying by the thickness, which we're just going to call dx, a really small change in x right here. So thickness is going to be dx. That takes care of giving us really the volume of one of those washers, and then my integral will add them all up for me. So I end up with something like this, and of course we can factor the pi out, so usually when I do this, I'll write it this way. And I'm really just trying to express, figure out how to express the big radius and the little radius. So in this case, we've just got straight numbers. So my big radius is always 3. Again, that's going to change as soon as I do some different curve where things are not necessarily just a straight horizontal line. So be prepared for that in the next one. And my little radius we said was 2. So that's going to be what my setup looks like. Oh, and I got to get my limits of integration are 1 to 4 or 1 to 5. I don't know if I did a good job explaining that in my other video. A way that I like to think of it, or that students have liked to think of it in the past, is where do your slices begin and where do your slices end? And your first slice is at x equals 1, and then you're going all the way. Your slices are all lined up to x equals 5. So that might be a nice visual for you. So I'm ending up with an integral from 1 to 5 of 9 minus 4, which is 5. So pi times 5x evaluated from 1 to 5, if I do my antiderivative, giving me pi times 5, which is 25, minus 5 times 1. So 25 minus 5 is 20, and there's my 20 pi, matching my first answer. But what we've built for ourselves is a system that we can use now if we don't always have that constant radius. So let's go ahead and try another one. And like I said, this one's going to be one that we can't use geometry for. We're going to have to depend on the calculus. So hopefully you're convinced that does work. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals radical x and y equals x squared around the x-axis. So, of course, I'm going to draw this first. Excuse me. So, y equals x squared generally goes up like this. And then y equals radical x. Kind of does the reverse curve. So, that's kind of my working picture for myself. And I'm going to revolve that around the x-axis. So basically, this is going to flip down this way, and this is going to flip down. I kind of think of it as a reflection. And if I'm making a three-dimensional, you don't have to draw the three-dimensional part. I'm just trying to help you kind of visualize this. It's sort of like a bowl, well, on its side, but if you turn it, it's sort of like a bowl with a real thick side at a certain point. And then it gets thinner at the top. So it is definitely hollow in the middle. And it actually could hold something. And then it's got, I don't know, I'm picturing when I was in a pottery class and learning to throw pots on the wheel. It was very hard to get an even thickness on the sides, and a lot of my pots probably look like this. So the geometry is going to fail us here. So let's jump straight to the calculus. And I'm even starting with that pi out front. And what I need to figure out is, okay, what's my big radius and what's my little radius? And I would encourage you to draw, to visualize, what if I were to take a slice out of this? So I'm going to take a random point and visualize taking a slice. So there's my slice, but in the middle here, we've got that hole. So when I pull that out, like I said, we usually describe it as a washer. But depending on where that slice is, obviously the outer and the inner radii get bigger and smaller. And sometimes there's a bigger hole in the middle. So what I need to do is figure out how I can express for any one of those slices what the outer radius and what the inner radius is. So my outer radius is going to be distance all the way up. That's this. And that's from my x-axis up to my curve, in this case, my radical x curve. So remember we talked about we could call this point x radical x, any point on that curve. And we're really taking the y value, the height of that point. So that's going to be my outer radius, is radical x. And then, of course, I'm going to square it in my formula. And then my inner radius is up to this point. And that is, so that's just this part here. And that is up to my other curve, which is my y equals x squared curve. So we could think of that point as x comma x squared. Any point on that y equals x squared curve. So the height there is x squared. And then, of course, like I said, I'm squaring that. And then my limits of integration. So I am starting my slices at 0, x equals 0, and going to the point of intersection between x squared and radical x. So if we're looking for a point of intersection, you might already know this if you're real familiar with these graphs. If not, we can do a quick solving here. Let's square both sides. So I get x to the 4th equals x. And I get x equals 0. Yep, that's one of the points of intersection. And then x cubed equals 1. Cube root of that is 1. So this is the point 1, 1. And like I said, you might just be familiar enough with those graphs. If not, a quick system of equations solving can help us find that point. So I'm going to integrate from 0 to 1. And that's going to be, I'm going to simplify this first. So radical x squared is just x minus x to the 4th. And now I'm ready to take it from there. So antiderivative x squared over 2 minus x to the 5th over 5, evaluated from 0 to 1. I'm just going to deal with the pi later. So plugging in the 1 squared over 2 minus 1 to the 5th over 5, minus plugging in the 0. Love it when that works out. When I have the zeros and everything cancels out. Be careful because that doesn't always happen. And I have 1/2 minus 1/5, it looks like, multiplied by pi. I guess I'll get common denominators there. 1/2 is 5/10, 1/5 is 2/10, giving me 3/10 times pi, or 3 pi over 10, for a final answer there. So not too bad, and hopefully that helps you understand just a slight extension, really, of our disk method. And I kind of referenced this in the other video that we call this the washer method, and it's really just when my disk has a hole in the middle of it. And that's why I'm going to be subtracting my radius squared minus radius squared. So for conclusions, I think we kind of already have a pretty good formula here. Volume equals pi times integral of r squared minus r squared. And then I just want to mention that that could be a dx, but that also could be a dy if I'm slicing it the other way. So recall that when we revolve around the y-axis, we do a horizontal slice, and my thickness is a dy, and that's about what we're about to explore. So let's go ahead and give ourselves a sketch for this. Give yourself some room because this one is going to be revolved around the y-axis. So y equals x squared. So y equals 2/3 x, some kind of a line. I'm doing an estimation here. Revolved around the y-axis. And I should have given you more information here. This would have to be given information from y equals 1 to y equals 4. Because this is not these two curves will not intersect each other again. So we're not doing like the region bounded by those two. So in this case, I would just be given what region do I want to find the volume of. So let's say that's my y-axis scale. So I basically have this kind of a section, and this is like solid. I always like to think of my visual that I use for myself is I think of it as like a clay object or some kind of a bowl, a structure. That's my solid. Anything outside of that is emptiness. So when I reflect it, I'm ending up with something like this. And I don't know if that makes any sense. So perhaps it's easier to see if we actually get rid of this line and this line. But that does show like the top of it, so to speak. So I've got this big bowl with kind of these chunky sides, but then this very fragile base. I don't know. I don't know what you'd use this for. But definitely a three-dimensional solid. To make this accurate with the description from y equals 1 to y equals 4, then I technically have it stopping down here. And I'll go ahead and erase just for the sake of, I would not be dealing with that part of it. So that is what I have going on here. And the geometry is going to fail. Obviously, this is not a perfect geometric shape. So let's jump straight to the calculus. And the calculus tells me, hey, you can take the volume by doing pi r squared minus pi r squared. You can pull the pi out. But this time it's going to be with respect to y. And the way I figure that out, so basically any vertical axis is going to be dy. Any horizontal axis of rotation is going to be a dx. But really it's a visual thing. If you think about taking a slice, so just think about a random slice here, and give your slice some thickness, so a little bit of thickness there, and then ask yourself, is that a small change in x or a small change in y? That's what the dx and dy represents, is the thickness of the slice. So this is a small change in y. And then, of course, we can hopefully visualize that if we pull that slice out, that is going to have a hole in the middle. And I've got to visualize what's my big radius here? And then what's my inner radius? So the big radius takes us to this outside curve is my line, the y equals 2/3 x. But that's really the x value. And I can't just put x in my formula because I got to be in with respect to y. So here's where I'm going to have to solve that. And if y equals 2/3 x, then if I multiply by 3/2 on both sides, that's going to give me 3/2 y equals x. So trying to get x by itself. So x in terms of y, because I really want x distance. That's what I've drawn in red there, is the x distance. I just need to have that in terms of y. So my big radius is going to be 3/2 y. Squaring that. And then my little radius is going to be to my other curve, my inside curve, which is the y equals x squared, but I need to get that in terms of x. So in terms of y. So x would be radical y. So that's going to be radical y squared dy. Integrating. So my first horizontal slice is at y equals 1, and then I'm stacking up a whole bunch of slices up the y-axis up to y equals 4. So I'm going from 1 to 4 are my limits of integration. And I should be in good shape there to go ahead and do the calculus. Well, I guess I'll rewrite and simplify for myself a little bit. So 3/2 squared is 9/4 y squared minus radical y squared is just y. And now I'm in a pretty good place to go ahead and find my antiderivative. A little bit of work, but not too bad. So 9/4 times y cubed over 3 minus y squared over 2, evaluated from 1 to 4. Let's tidy that up. So it's really 3/4 y cubed minus y squared over 2. So I need to plug in my 4. 3/4 times 4 cubed minus 4 squared over 2. Plug in my 1. 3/4 times 1 cubed minus 1 squared over 2. So it's going to be 4 squared is 16 times 3 is 48 minus 16 divided by 2 is 8. So that's 40. and then 3/4 minus 1/2 is really 1/4. So 40 minus 1/4, I guess I'll put that over 4. So times 4 and times 4 is 160 over 4 minus 1 over 4 gives me 159 pi over 4 units cubed. Oh, that was some fun calculus. Okay, so we're going to do one more example and then call it a day. And the last example we're just going to set up. So I want to take you one other place with these, but also give you a chance to practice a little bit more what we just did. So the one thing that we haven't talked about is revolving around axes other than the x and the y axis. So we're not going to go too crazy. We're going to stick with vertical and horizontals. But we can revolve around other axes, and I want to kind of dip our toes into looking at what that looks like. This is very much a visual thing, and it's all about figuring out what the radius is. So join me and let's do, here's the problem. So we're going to deal with the region bounded by y equals x squared, y equals 4, and x equals 0. So that actually does make an enclosed region, and we'll look at that as we kind of jump into this. We're going to revolve it around 4 different axes. So let's actually start with x and y axes, and then we're going to do 2 other axes, another vertical and another horizontal. So I think the easiest one here is actually the y-axis. So if I'm revolving it around the y-axis, let's take a look at what this curve is. Y equals x squared. Basically, it looks like that. Y equals 4. So we have this point 2 comma 4. Then I'm going to go ahead and identify as the intersection point, and then x equals 0. And that's kind of like the inside of my previous problem. What was the hole is now the actual solid. So that is my solid, and if I revolve that around the x-axis, I end up with a solid here. So I was going to say bowl, but it's really not a bowl because there's no empty space in the middle. So whatever we call that, that almost looks like my half of a lime, a solid thing. So the first thing I'm identifying is this a washer or a disc? In other words, is there a hole in the middle? And because that whole thing is solid, if I take a slice out here, there's no hole in the middle when I bring that out. And I'm also recognizing that there's a thickness with respect to y, a small change in y, and therefore this is going to be a dy problem. Okay, so anytime we're revolving around the y-axis, we're slicing horizontally and ending up with dy. So volume is equal to my general formula here, pi times just radius squared and dy. Now let's put in my details. So integrating, well, my radius I need to figure out. That's the x value on this curve. But I can't just put x because I'm integrating with respect to y. So everything has to be y, which means I'm going to use my alternative here, x equals radical y. And then my limits of integration, well, I'm starting at 0 and I'm going up to 4. Think about all those horizontal slices. So I'm going to go 0 to 4 for my limits of integration. So that is my y-axis. Now let's compare, let's take the same region and let's revolve it around the x-axis. And you'll notice a few on your My Math Lab that have you do this. This is a good chance to kind of get familiar with differences here, what's happening. So same region, this is 2 comma 4. And if I reflect it, I end up down here. And I don't even know what to say this. I guess it's a bowl. It's got a cylindrical outside and then kind of an inverted space in the middle. So it wouldn't be too practical. I don't think it'd hold a lot. definitely, so asking myself 2 questions, am I integrating with respect to X or Y here? And then do I have a washer or a disc? So I'm integrating with respect to X, drawing the slice, I've got that dx, and then I definitely have a hole in the middle here. So this is going to be a washer. So I'm thinking 2 things. I'm thinking volume equals pi times r squared minus r squared, and then I'm thinking that has to be a dx. So you don't have to write that, you can just think it, but I absolutely consciously think about that, and that kind of guides the rest of what I'm doing. Okay, so for my big radius, well, that's the distance from my x-axis up. And I kind of picture sliding that along. And at all points, that's actually going to be the same value. Or you could think of it as one of your curves. You have this y equals 4 and this y equals x squared. And those are your 2 curves. And the other one we had y equals x squared and y equals radical x. And those were our 2 curves. So this one might feel a little bit weird because our top curve is a constant. It's 4. And it's always 4. So that is me putting in my function. It's just my function is y equals 4. And then my inside curve, well, that's my distance from my x-axis up to that x squared curve. So that's going to be x squared. And that would be my setup. Oops, I need my limits of integration. So I'm starting my slices at 0 and going over to, not 4, that's the height. I'm going over to 2. The last slice is going to be at this x value. That would be right here. Okay, so pause and process if you need to. If you're ready to move on, here's where I want to expose you to just the last variation of these questions, really, that we'll look at. And that would be other lines. So let's start with the line y equals 4. I want to revolve around that line. So that is a horizontal line. And therefore, that's going to behave sort of like the x-axis, which is also a horizontal line. So let's kind of sketch this out. So if I'm revolving around the line y equals 4, that is this line right here. And therefore, it's going to spin up and kind of make a hemisphere, kind of, not exactly perfect, part of a lime or lemon, something along those lines. So 2 questions I asked for myself: is it a disc or washer, and is it a dx or dy problem? And our answers to this should be, it's a disc, not a washer, because if I slice this, there's no hole in the middle. It was a solid region, and it's going to be solid when I take a slice out. So there was no hole in the middle. You can kind of shade in that region if that helps you. So it's just going to be a 1 radius squared. And then my slice is a small thickness with respect to x. I'm slicing it along the x-axis. So that's some small change in x for that thickness that we're visualizing right here. So that's going to get me started, and now I just need to figure out what is that radius that I'm squaring. And then I'm going to be integrating from 0 to 2, very much like the previous one. So notice that when I had an dx there, I integrated from 0 to 2, and same thing here. So my radius is a little bit tricky here. This one's kind of maybe going to drive you crazy. So here's my radius. So the radius this time is not going from my x-axis to something. It's going from my line y equals 4 down to something. Down to that point on the curve. So you need to think of this as points on curves. X and y values are heights and distances. So what I'm going to say is, and maybe picture moving that line too, and picture all the different spots we could end up at, all of our different radii. And our radii are always, I'm going to pose, always going to be 4 minus something. And the reason I'm phrasing it that way is because this distance down here, this distance down here, which I'm drawing in yellow, that is actually what I can define. That is the height up to my curve, and that's my y value that we talked about. So if we have this point x comma y equals x squared, that y is the x squared part. So my radius is actually going to be the entire distance there, which is 4, minus the x squared. So this entire distance is always 4. And then I'm subtracting off that yellow piece. I don't know if that makes any sense. So I've got like this distance of 4 that's made up of x squared. That's the distance up to that curve at some point, and then the rest of it. And this is my radius, but it's really the difference between 4 and x squared. So my radius is 4 minus x squared. That's before I square it. And that's a visual thing, and that's kind of hard to wrap your head around. So I hope that made a little bit of sense as far as a visual. These do get a little bit tough. And we're going to do one more. So this one is going to be the line x equals 2. And this is a vertical line other than my y-axis. But this is going to function very much like my y-axis. So let's take that same curve that we have. You guys have that region memorized. It looks like this. And the line x equals 2 is this right here. So I'm going to reflect and this is kind of like almost like the same as what I had around my x-axis in terms of like the shape. So the solid part is all of this being revolved around, and then there's like emptiness in the middle. Okay, versus this one, which was all solid. The whole thing. So this is going to be a washer. And this one is going to be a dy. And the reason I know that is if I visualize a slice here, there it is. The thickness is a small change in y. I'm doing a horizontal slice. That's the only way I can get the circles. So when I'm visualizing this, so my slices are going to be stacked up this time. So I'm going to go 0 to 4. I'm back to horizontal, and this is going to be very much like my y-axis, which I'll show you in just a second, the comparison. And then I need to figure out how to express my big radius and my little radius. So again, I'm going to draw a picture here. I'm going to start with my original region. My big radius is going to be 2 always. Picture moving that up and down. Picture taking a different slice here, and the big radius is still 2. So I've got 2 for my big radius, and then my little radius. Here's where I'm going to have to be a little creative. The little radius is that inside part. So if I kind of picture this slice, the little radius here is actually the difference between, we had 2, and I'm going to take away the distance over to my curve. I guess I'll draw it in here. So I need the leftover part. So remember, this we've been calling x, right? So x, except in terms of my my function here, x was radical y. So even go up to this one, and we used our radius was radical y right here. That's what we had there. So now it's like I've got the leftover part when I take 2 and subtract radical y. So that's radical y. The whole thing is 2, and I want just the leftover part right there. So I'm going to call that 2 minus radical y for my inside radius. And that entire thing is getting squared. Okay, just to do kind of a quick comparison here, because I did the others in a row and made a comparison there. Let's look at the fact that this one's a dy, just like this one, and my limits of integration are the same. Okay, so when it's a dx, you're going to be looking for those x values. When it's a dy, you're going to be looking for the y values. When you're trying to figure out the radius, good luck, draw a picture. It's not easy, but we will practice them more and you will get better at them. So thanks for sticking with me. I hope that made a little bit of sense. Good luck with your My Math Lab practice. Follow along. I think it should match up pretty well with what we just practiced.